everybody. I think we're going to get started momentarily here since it is exactly 4 p.m. right now, and that's our nominal start time. So unfortunately, I don't have the standard slides up, but the main one I wanted to mention is that there is the usual code of conduct here, and so everybody should be respectful and abide by that throughout the presentations and any discussion we have. The way the session is going to work is that we have 5 presentations. Each presentation is allotted 12 minutes for speaking and then 3 minutes for any questions that may arise from the audience. The theme of the session is stellar science and crowded fields. So we'll hear about things like stars in the Milky Way galaxy, and also a little bit about techniques for how to do stellar science, for example, in crowded fields like you would have in the plane of the Milky Way. And so the first presentation, we'll bring up Tom Wilson, who's going to talk to us about beyond the centroid, how to do, astrometric uncertainties and deblending.
Okay, so everybody, guessing in the room, you should be able to hear me because the air is propagating my voice. Can everybody hear me online and see the slides? I guess if you can't hear me, that's not very useful. Yes, thanks for coming today, and thanks for having me to talk about the need for a slightly more complicated model for astrometry in the era of LSST. And I like the fact that we can say it is the era of LSST because it genuinely will be, which is nice to not just, say that slightly unnecessarily. Starting with a photometric catalog. If somehow you maybe have amnesia, this is your first day back trying to become an astronomer again, a photometric catalog is the positions and brightnesses of all of the objects in your images. What the telescope will do is take a bunch of pictures. Here, I just got one from WISE because they had a nice cutout service. And what we do is we run our pipeline, and of course the team have spent countless hours creating a very nice pipeline for extracting the positions and the brightnesses of our objects. So we have one in there and a slightly less bright one there, so they have some brightnesses. You get some sort of uncertainty in that. I'm not going to talk about that column today. I want to focus on these 2 columns here. The position, which I'm going to represent in this talk as a little black circle, and the uncertainty, this is a thing I'm going to talk about almost all of today, is my rainbow circles, which is, as I accidentally, during my thesis, started calling the astrometric uncertainty function, and then discovered historically that's what Gauss called the Gaussian before it was called the Gaussian, the astronomy error function, which was just a nice historical happenstance. What I want you to think of this as is the certainty with which we think we know the true position of our object, given where we measured the object to be. So that's what our black circle is. And then we have this decreasing probability, which if I then slice this in 2D, you see I have some probability density functions. It is the probability of the true position being this far away from the measured position, and it should decay in some fashion because we hope we've measured the best possible position of our object. And of course, what most people think of when they think of uncertainties is what I'm going to refer to as the centroid uncertainty, or perhaps the centroid precision, where what we have is we have, again, a 2D slice through our image now, an increase in counts as the star or your object, or whatever it is, increases. Each of these is a pixel. And then we fit our model to these data. And you have, perhaps traditionally you have some sort of reduced chi-square, and you see that it reduces, and there's some minimum, which gives us our best fit. That's where our black circle was before. And then you have some contour, some chi-squared plus 1-esque cutoff, and that gives you the error bar that we think of as the uncertainty of our centroid, which then generally is represented as some nice Gaussian function with, you've got some position, you've got a mean position, and then you've got some covariance matrix to describe the certainty with which you think you centroided the object, measured the position of this object on the detector. But I'm going to be slightly dramatic here and say basically all literature to date assumes that that position is that is the only source of uncertainty in these images in the pipeline. And there's a random couple of examples there, but there are countless more. But the astrometric uncertainty function can be of any necessary form. And very briefly, I'd like to just go through a few examples of this. The first one, perhaps the most obvious, that we almost don't realize is a source of systematic uncertainty in our positions, proper motion, where we're all very familiar these days with Gaia, which has measured proper motions very exquisitely for the brightest 1.5 billion or so sources on the sky. But LSST will also get proper motions, except at some point even it won't be able to measure proper motions, below the single visit limit of 24th magnitude or so. You just won't have the signal to noise. So therefore what you can do is you can model this statistically, where my random examples here are, the data points are Gaia observations, and I fit a nice model, essentially to the motion of the galaxy, just rotating around the sun more or less. And I can propagate my position in 2015 through a decade to today or to the start of LSST. So I can take, for example, my WISE object and I can forward it through time, but including all of the possible motions that it may or may not have, which I don't know because I can't measure those motions at 25th magnitude. And what this does is it translates our object, so the object has physically moved, but it also increases the uncertainty, decreases the precision that we have of where this object is in 2025. Of course, we can also do this with weakly constrained proper motions because we have another covariance matrix which we can combine with our centroid precision in the first place. Another nice example is DCR, which is, in a nutshell, where the object is measured in a different place because the atmosphere of the Earth has refracted the object, which DCR stands for differential chromatic refraction. This happens at different amounts at different wavelengths. And we have some function here, which is a factor of the band, the filter that we're in, and the color of the object. And what this essentially does again is it translates the object. We have to correct this and subtract it back out effectively. So we have some translation of our object's position and an increase in the uncertainty of its position. But the main uncertainty in the era of LSST takes a little bit of explaining, so I'm going to run up at it from slightly further away than those other two slides. It's crowded fields, hence the title of the session in which I am speaking. But what I have here is I have a random Gaia object, and I've asked where are all of my WISE objects, because that was largely the data sets I dealt with during my thesis, within half a minute of it. There's one at the origin, that is the counterpart to that object that we've detected. And then there are some random friends completely unrelated somewhere in the sky nearby. I add two more sources. You can again see you start to build up some things at the origin and some things randomly near it. I do this for, I think it was 15 square degrees, some number of square degrees on the sky, and you get something that looks like this, where here you now start to build up the density of objects on the sky, randomly distributed. In the middle, you have all of those counterparts to the Gaia sources, but there's this density, there's this dearth of objects here. And what was that? We spent quite a while puzzling over what that was, until you realize that's the size of the stellar PSF for the WISE telescope to scale. What happens is the objects that are here are hidden by this very bright object that's in front of it, and they get absorbed into the measurement of the brighter source. What you are actually measuring is the brightness of two objects. You've now got a composite object which contains a hidden, unresolved contaminant source. Where what happens in the background here, we've got a picture of the WISE, a picture that the WISE telescope has taken, and laid over the top of that is the detections that the Gaia and WISE surveys have actually found in their pipeline. And you can see there's an extra WISE detection here that we don't find with, or there's an extra Gaia detection here that we don't resolve with WISE, but depending on the quality of the TV and or the screen share at home, you can see there's a slight elongation of the WISE object. WISE just wasn't able to resolve this, but Gaia found it, and it caused a perturbation in the measurement of the WISE detection. So contaminant is now off the screen to the top left, because I've rotated the image around, and it's caused an additional tug in the measured position. And what you can do with this is you can essentially simulate your entire sky. So you have, on the left-hand side here, I have logarithmically the number of counts per unit magnitude per unit square degree as a function of the brightness of the objects. And I have my very crude approximation of a PSF, a circle. And say, oh, I found, just through Monte Carlo simulations, there's an object here that's reasonably bright, it's only 0.2 magnitudes fainter, and it's there. And then I don't know, there's another couple that are a magnitude fainter, let's say. Then I have to calculate what this would do, what effect this would have on the measured position. I've got two choices. One, nice and simple. I treat my objects as point sources, and I just do some statistical weighted mean. That's applicable in the very high signal to noise range or for aperture photometry. Or I've got a slightly more complicated algorithm on the right-hand side here for the low signal to noise background dominated but PSF regime, where what I'm doing is I'm minimizing my chi-squared, maximizing my log likelihood for fitting one PSF to multiple data. Yeah, if you can see here, I've added an extra little Gaussian down there. And very briefly, because I know I'm running out of time, this also has an effect on the photometry that you measure, not just an astrometric perturbation, there is a flux brightening in these objects, where in the aperture photometry case, it would just be a naive sum of the hidden flux, but it's a slightly more complicated case for the Gaussian in the background dominated PSF photometry case. But once I've done this, what I actually get now is I don't get a translation of my measured position. I just get an increase in my statistical uncertainty. Sorry, I add a systematic to my statistical uncertainty. So I get a broadening of my rainbow circles down here. And you can see for Y's, as an example here, this has a significant effect where we find that if you don't include this effect, you miss 1 in every 2 Gaia Y's matches in the galactic plane, which should concern you when I tell you that LSST will have as many sources per PSF area as WISE does in the galactic plane at 10-year depth. And again, as I show our simulation that we have run of this in the top right-hand corner now. Oh, no, there we go, I've already said that. You see that my red dashed line does not fit particularly well my blue circle, my blue solid line anymore. And this effect will overwhelm centroid precision. Basically, we do too good a job of measuring where we think the object is that we now have to measure, we have to account for the fact that the object isn't actually where we think it is. And with that, I will leave up lots of words for my conclusions and take any questions. Thank you.
Yeah, we have 3 minutes for any questions from the audience. Knut?
Yeah, so for the effect of the confusion on fluxes, does it necessarily always have to be brightening the source? Because when you're doing photometry, right, you're comparing the flux either within an aperture or fitting a PSF to the background, right? And if the background has sources in it, right? So if for instance, on the scale of your resolution element, it turned out that you had fewer sources than in the background, you could actually get a decrease in the flux as well. I agree that
but that's true. But that's always going to be the case anyway. If you had an unconfused source and your background subtraction was wrong,
yes,
then you'll over subtract. But with this, you under over subtract in that case still. It's I think it's always a positive effect.
Yeah. Yeah, but I agree that it's the fluctuations basically due to confusion sources within the scale of the resolution.
Well, it's this. You've added these 2 red lines together and you've got a black line in there, and you're trying to fit that with 1 gray line.
Yeah, right.
But I think in your case, if you were going to over subtract the aperture you were taking, say, around the outside, you'd under over subtract that because of the extra source. So it's always a positive effect. Even that is a problem, yes.
I think Avi had his hand up first, so maybe we should go to Avi first.
You need to come over here. There's no microphones in that half of the room.
I have a loud voice. Can you hear me?
I can, yeah. I just don't know if they can.
The microphone won't pick it up.
Yeah, for the people online.
Where's the mic?
Just in the sky. Just come to this half of the room and then talk. It's fine.
So I was just going to ask you about Rubin being a ground-based facility with a wide field with short exposures. How does the atmospheric turbulence shift or move part of the image with respect to the other?
Have time.
How does that?
I don't know because that's Bob's job largely. Bob's in charge. I don't know. That's a good point. That will do something, but similar with DCR, you essentially hope that the pipeline team have dealt with that. I just mentioned it because it was interesting, but that is yet another term that if it was not accounted for, would do something like you translate your object position and you increase your uncertainty. I don't know how, but we could find out together.
There is data on that from the dark energy survey. There is, I mean, there are data from for that on the dark energy survey. If you look at the astrometric paper on the dark energy survey, like there is I mean, so it's a longer exposure, shorter, I mean, smaller aperture. But like from the top of my head, like distribution from atmospheric turbulences, it is like 10 arc seconds, or something, 10 milliards seconds, like on the dark energy survey.
Yes, somebody will know. I don't personally know, but that's because I wanted to talk about this thing mostly. Please look at these slides instead. They're the important ones for LSST. The others will be handled. You'd hope turbulence is understood and is accounted for within the pipeline. But if it isn't, or the nice thing is because we can compare to an external data set, you know, say Gaia, for example, we could model the distribution you see of the separations between objects measured in Gaia versus the same object measured in LSST. And if you have accounted for everything else, you can see whether that's a problem. And that's something we plan to do with commissioning data.
I've done that. We can talk if you want.
You can also post the link to whatever dark energy survey papers there are on the Slack channel for this as well, if people would be interested to see those. One more question?
Yeah, sure.
Okay.
So I was wondering how the severity of these perturbations and the frequency of these perturbations like changes with galactic latitude, like for more extragalactic pointings. Is it still pronounced?
So in terms of a 2 arc-second circle, in the galactic plane, you're looking at maybe 10 objects cumulatively. If you integrate down to 27th magnitude, there will be something like 10 objects at every random pointing, but in the extragalactic scale, it's more like 1 or 2. So it's a factor several less, but it's still not none. This is not the right version of the talk. I have a slide that shows that for at least for WISE, granted WISE is infrared, so it's seeing galaxies more than LSST will, you see a statistically significant deviation from the centroid component of the AUF still. So it might be of order 10% non-Gaussian wing, maybe, something like that.
Okay, yeah, thanks again, Tom. So let's thank Tom again, and then next speaker is virtual. It's Alex. Razim. Alex, could you unmute yourself and okay, great.
Okay, so you should see the slides and you should hear me, right?
Yeah, do.
Okay, excellent. Thank you. So hi everyone. And this talk is about deriving synthetic LSST magnitudes from the Gaia XP low resolution spectra. And just as a refresher, let me move this panel somewhere. Just it didn't yet. So just as a reminder, so Gaia, everyone knows, an excellent space telescope for obtaining mainly high precision astrometry, but also a lot of additional data, for example, photometry, and also low resolution spectra. Obtained with 2 spectrographs on board for over 220 million sources in this data release. Depending the magnitude range that is brighter than what is expected LSST to be. So LSST will be already saturated at the magnitudes where Gaia is the most comfortable. So these spectra are low resolution with variable resolution, and they cover the wavelength range which is mostly overlaps with the LSST band passes, but not completely. And considering that Gaia is more bright than LSST, it is curious to see whether we can obtain synthetic magnitudes that can be combined with the future LSST magnitudes. And in this way, we can get an extended photometric data set that ranges wider range of magnitudes. And with these high quality synthetic plus observed magnitudes, we can do more science on specifically Milky Way structure studies and other astrophysical studies. So the idea is, let's get this synthetic photometry and let's in the future use it for all kinds of science. However, there are some issues, and this is that these spectra, they are known to have a number of systematic and random biases. So the Gaia XP, the Gaia team have developed a package Gaia XP for obtaining these synthetic photometries, and they compared them with different already observed photometric data from SDSS, DES, and so on and so forth, and discovered that there are some magnitude-dependent, core-dependent biases, and also random scatter that is obviously larger for the fainter object. So if we want to use this kind of synthetic magnitude for any kind of high precision science, we want to correct for these biases. Gaia XP people, they did it in the following way. They used stripe 82, they used the SDSS stripe 82 high precision photometry, and they compared the synthetic photometry and observed magnitudes, and then they corrected the SDSS filters, assuming that kind of Gaia is the perfection and SDSS filters aren't as precise as we would like to have them. However, what we want to do is we want to try obtaining synthetic photometry before we have real LSST observed data. And besides that, considering that we also know that Gaia XP spectra have their own biases, that we do not quite, I mean, you can believe that it's Gaia that is more biased or that it is SDSS more biased, but we would like to take our ground-based observations as ground truth, because at the very least, for the ground-based observations, we can fix our instruments if we detect some biases, while Gaia is in space. So whatever is wrong there, it is already unfixable, essentially. So the Gaia XP team tweaked with the SDSS filters, but we cannot do this. We need to fix the spectra itself. And it is more complicated than tinkering with the filters, because if you correct one part of the spectra, but it affects photometry in the adjacent bands. So it is a multi-dimensional problem. So we did a number of things to improve the situation. We once again use SDSS stripe 82 data. So we believe that they are the perfection. We compared the synthetic SDSS data with observed SDSS data. Then we find the corrections for the spectra. And from these corrected spectra, we can obtain synthetic LSST magnitudes. There are several corrections that we can should implement. So first of all, Gaia XP spectra, they do not cover the full wavelength range. So at the U and Z or Y bands, there are some lacking photometry. So we should add this photometry, and we are doing this by adding the adjacent and adjusted synthetic atmospheric model spectra from Kurz. We select these models using Gaia astrophysical parameters that are also obtained from the Gaia XP spectra. Then we are using a tinkering mechanism that I'm going to describe in a few seconds. So these systematic corrections that are magnitude and core dependent, they turned out to be pretty complicated, and we tried to correct them with a number of things using machine learning based approach, using different approaches with wavelets corrections, simple polynomial fittings, and so on and so forth. And originally, we hoped that we will be able to correct the spectra in such a way, so using a kind of narrow corrections, hoping to fix the sources of the highly random noise that are present in certain parts of the observed low resolution spectra. So this noise appears as a result of instrumentational high frequency noise that after the converting the spectra from the continuous form to the sample form, they get amplified in a random way. So they are pretty hard to correct in a systematic way. So we hoped that we will be correcting this spectra only the most problematic parts of the spectra, and then we will have higher quality spectra that are already very good. And that would be applicable not only for obtaining synthetic photometries, but also for other kinds of sciences. So maybe even kind of making higher precision measurements of the emission lines and so forth, and so on and so forth. However, as it turned out, this kind of corrections, this is what we were doing with, for example, approaches where we tried to produce correction curves as a sum of narrow Gaussians. It turned out that this approach works for high signal-to-noise ratio data, but for lower quality observations, it just doesn't work. The levels of noise too high. So we turned to another approach. Essentially, we put all the observed spectra on a two-dimensional grid, photometric. So x-axis is Gaia BP magnitude and y-axis is G magnitude. Actually, we can also use different magnitudes or even cores, but it doesn't affect the results that much. So on this picture, on the right hand on the top, you can see the counts that are correspond to the number of spectra that fill in each cell on this grid. Then for each of these grids and for each band, so all grids Y, well, all grids for SDSS, we calculate the median magnitude residual between observed and synthetic spectra. And this median magnitude residual can be turned into a correction coefficient for the fluxes. And then we just multiply, so for all the spectra that fall within this cell, we multiply the part of the spectra that corresponds to a given wavelength to the given band, we multiply by this correction coefficient. And it turns out that there is no need for any smoothing, for any interpolation between the bands, because really the differences between these correction coefficients isn't so big. But essentially for each cell, we have 5 correction coefficients for all the spectra that fall in this cell. So what are the results? So here is a bit of illustration how the extension is happening. So we have a low resolution spectra. You can also see the high noise region that are mostly present on the edges of the spectra. Obviously, this is expected. So, and then there is a missing fluxes, missing in terms that the wavelength coverage isn't complete for the SDSS. So we find the best fit synthetic Kurutz model. And then we either extend our observed spectra or even cut these high noise regions and replace them with synthetic data, which actually proved to be a good idea. And actually, the best quality photometry that we get is when we replace almost completely the observed spectra in the U band, because it is too noisy. And then this is the corrected spectra. So blue line is the original spectra and orange one is the corrected. This is after this correction coefficient that we obtained on the grid. So the difference isn't so big, but the results in terms of photometry are very good. So on this plot, this is for U and G bands. On the left column, you can see synthetic magnitudes that are obtained without any kind of correction. So you can see that there is a magnitude trend in U band, magnitude trend on G band. There is noticeable median differences. On the center is Gaia XP synthetic magnitudes produced with those tweaked SDSS filters. And on the right hand is our corrected magnitudes. Now here it is not really noticeable. On color marks, it's probably even clearer that the color trends are going almost non-existent. And actually, it is probably the best noticeable on the beam statistics. So for the U band, median residuals are compared between our correction and Gaia XP correction for the tweaked filters. But for the G band and actually for all the RS band, our correction outperforms Gaia XP noticeably. So it turned out to be a very good approach. And just for illustration, our previous methods, we significantly improved the results compared to our previous methods. Unfortunately, the scale isn't the same because I just taken the picture from my one of my previous presentations, but pay attention to the numbers to the y-axis. So if before we had average median magnitude that was of order of 0.01, then now we are routinely going down to 0.001 if we are lucky. So for the RYZ bands, the trends are significantly, I mean, they turn to almost non-existent. We cannot do much with the random noise, unfortunately, but median residual goes close to 0. This is old result, but they are not so interesting. So this is just for illustration how it looks on this magnitude grid. So essentially on the left column are the counts of the objects per cell. On the center is the median residual that we used for calculating the correction coefficient. And on the right are correction coefficients themselves. So 1 row per band. And actually for all bands except for U band, the correction coefficients and the medial residuals are pretty smooth. So there is the only issue is with the U band, which is indeed there are regions of significant differences between these median residuals, which is mostly related to the low quality of the data, of course. So RYZ bands, they are pretty smooth. So as a result of this correction, we are getting synthetic corrected, spectra for almost 200 millions of sources for low resolution spectra. And for all these sources, we are getting synthetic LSST magnitudes and synthetic SDSS magnitudes, of course, because this is what we are using for correction. And for now, we are pretty happy with the biases. They look almost non-existent. And we expect to calibrate this data in addition on the LSST data when they are available. And right now we are still correcting, we are still trying to figure out how to produce a reliable synthetic magnitude errors, which is not really simple considering that with the number of additional corrections that we introduce, the original flux errors, they become not so significant as the errors that we introduce. So we are still not sure whether we are going with the theoretical magnitude errors or we'll just using empirical ones obtained from the comparison with the observed stripe 82 magnitudes. And I think this is it. And I think that I am out of time. So thank you.
Yes, we have 1 or 2 minutes for questions. Is that Douglas over there?
Sweet spot.
Just anywhere in this room.
Okay. That's a great data set. Do you plan to also publish, or do you have available the corrected or the corrected Gaia XP for general use? Because one can see that the possibility of using it not only for synthetic LSST magnitudes, but say synthetic Roman magnitudes, synthetic Euclid magnitudes, and so on, and doing and be able to create transformations between the different systems, which become very important as we move forward.
Oh, yes, absolutely. So we are planning to publish not the corrected spectra itself, but correction coefficients. And then obtaining the corrected spectra is going to be just multiplying the spectra by this correction coefficients. It's simply for the, space storage, because it's easier to publish 5 numbers than the whole corrected spectra. But yes, it's going to be public, of course.
And the code to apply the corrections.
Yes, totally.
Great, thank you. Thank you very much. Looking forward to that.
Thank you.
Are there any more questions for Alex before I begin? Okay, then I'll start sharing the screen here. Alex, could you stop sharing your screen?
1 second. Yep.
Okay, thank you. Okay, well, that worked. All right, yeah, so my name is Aaron Meisner. I'm a staff astronomer at NSF NOR Lab in Tucson, Arizona, where I work on the Rubin community science team. And I'll be talking today about my own scientific interest, which is searching for halo T-dwarfs within the Rubin LSST dataset. So just to start out, one brief motivation about why would you even want to study brown dwarfs in general. We think that T-dwarfs and also halo T-dwarfs are brown dwarfs rather than low mass stars. So that's why we're talking about brown dwarfs here. First of all, there are lots of brown dwarfs. There's 1 per 4 main sequence stars. This number was actually recently revised to be even more heavily tilted towards brown dwarfs. It used to be more like 1 per 6 main sequence star. Doing more and more of them as we look deeper and deeper with more red optical and infrared data. There's the question of the initial mass function. So you can use these objects to bridge between the smallest red dwarf stars and giant planets, like we see in stars around our own, around stars other than our own. It also tells us about the process of star formation at low mass, for example, multiplicity, and also if you have multiple star systems in this low mass regime as a function of, say, mass and separation, how commonly do they form? Brown dwarfs, you can see them far enough away. They're very good tracers of galactic structure because they're long-lived. They don't go supernova after a certain number of millions or billions of years. They pretty much just cool gradually over the entire history of the universe. And they're also interesting as exoplanet atmosphere analogs because they overlap in temperature and sometimes in mass also with exoplanets. But you have the advantage with brown dwarfs that you're not being outshined by the bright light of a host star nearby it. I'm going to talk a little bit about what I mean by halo T-dwarfs. This is a very recently discovered population of objects. It's mostly been discovered by citizen scientists working on a project called Backyard Worlds. And so some of the terminology is along the bottom, but for low mass stars and brown dwarfs, we have these terms that are subdwarf, which means a metallicity of like -0.5 dex, extreme subdwarf, which means a metallicity of -1 dex, and ultra subdwarf, which means a metallicity of -1.5. And so those sort of -1 to -1.5, you're starting to get into halo metallicity territory rather than thin disk, which would be more like metallicity of 0, and thick disk, which might be a little bit metal poor, like subdwarf, we call it. So metallicity of -0.5. These are the first 2 extreme T subdwarfs, we call them. So these are objects with temperatures below 1400 Kelvin, we think, and metallicities of -1 or lower. These were only discovered in the past few years by, again, volunteer amateur astronomers. And what you can see is that they have very anomalous spectra shown in the black as compared to, these are some spectral standards comparisons, I believe. Even qualitatively, they don't really fit anything like what we've seen before. And they're also a very poor fit to models. So you can try to overlay some models and you can draw some general conclusions, but even qualitatively, the models don't fit very poorly. So this is kind of suggesting we're getting at something interesting as far as like the atmospheric physics of low temperature objects that we haven't seen before. And so far, we've mostly been doing this all in the infrared rather than the red optical. I'll get to LSST in a moment. The way we've done this is mostly discovering with WISE, where it has these W1 and W2 bands that span from 3 to 5 microns. And then we also have the J band for this. And you can see that empirically, we drew this hatched gray box. That was our color selection for these objects. And generally, there's this nice curve where the L and T dwarfs follow, but then there's this kind of middle ground where all of a sudden it's being populated now where it hadn't been populated before. And we think these are the low metallicity T-dwarfs that we just hadn't been able to detect before. And indeed, we should have done this part first, but actually we did it after the fact. We looked at the models. We made a new grid of models produced by Mike Line and published in one of my papers. And we looked at the temperature tracks as a function of metallicity. And we saw actually, if you look at this, it makes sense that the temperature sequences start to shift gradually over towards bluer colors on the x-axis. And so this kind of confirms the idea photometrically that we're searching for what we thought we were searching for, cold low metallicity objects. Just a few words about these models, because I think these low Z models that we published specifically for this work are very interesting. It's a huge grid of low temperature models, more than 8,000 models in total, spanning a really wide range in metallicity from -2.5 all the way to +1. And we made these publicly available as well. So as I'll say in a few moments, this will be very interesting for trying to make predictions about or understand what we see in terms of the red optical color of very cold halo objects in the LSST dataset, because these models go into the optical as far as their wavelength coverage. So just to show you the early days state of affairs we have with these halo brown dwarf situation right now, we really need more examples in photometry, which is where LSST is going to come in, I think. So right now, this is really all that we have in the optical, and some of this is actually infrared, not even optical, right? So there's 1 I-band detection and 2 in each of Z and Y, and these are also mishmashed together from all different surveys. And so it'll be great to have a really uniform data set of about 100 of these objects with LSST photometry, as opposed to a couple objects with a mishmash of follow-up and a few data points here and there. So even though we only have very limited information about this population, we can still make some predictions for what LSST will see. One challenge there is that only one of these halo T dwarfs that we know about actually has a parallax right now, actually has a distance known, so that makes it a little bit challenging. But we think that basically with Ys, we're able to go out to about 40 parsecs. But with LSST Y-band, we should be able to detect them out to about 130 parsecs. And so when you factor in sky area, that means we'll get about a 15 times volume enhancement in our search for these halo T dwarfs with LSST as compared to Ys. Perhaps kind of interestingly, the Euclid wide survey J-band distance limit is very similar and well matched to the LSST Y-band limit for these objects. So that suggests a good complementarity there. Of course, in addition to colors and photometric detections, you also will have a lot of astrometry from LSST and Rubin. And so just doing some simple math here, if you look at 130 parsecs and say a halo-ish type of tangential velocity of 100 kilometers per second, that's 160 milliarc seconds per year, which I think should be very readily detectable with LSST. And I know LSST is aiming for something like a parallax uncertainty of 1 milliarc second, in which case we should also be able to do parallaxes for pretty much all of the objects that we detect, although I guess these will be low signal, so we'll have to look at that in a little more detail, but parallaxes seem at least on the table, I guess I would say. And so, yeah, currently we have 6 candidates. And with LSST, if you just multiply by this factor of 15, we should get to about a factor of 100. And so that will be a really great step forward in the study of this population. One thing that I think really needs a lot more work in the next year or so to get ready for all this LSST data is to understand what do we actually predict to see, or how are we going to select these objects out in our surveys, particularly LSST, because here's a little exercise I did where I took all of these LOSI models, I ran them through some synthetic photometry code, synthetic color creating code, and there's basically, you see a bunch of temperature tracks at different metallicities, and those are represented in different colors. And this is Z minus Y on the vertical axis, so a fully optical color, and then a partially optical infrared color on the horizontal axis. And so what this tells me is that as a function of metallicity, you definitely see noticeable imprints on the color of your objects. But still, I think the more important question, which I don't think anyone has really looked into fully yet, is how do you, or can you distinguish these objects based on their colors from other background populations that are much, much more numerous, like stars and galaxies? And so I think that would be a really great exercise to do, being ready for early science, to understand how we're going to select these out from the tens of billions of normal stars and galaxies that, for the purposes of this search, are background objects. So yeah, there's just a few more slides. I wanted to highlight a couple of exciting things going on in this area of science, substellar science, where we're looking for low temperature, low metallicity objects. As I said, it's very early days. So a lot of times we don't really know exactly what we're looking at or what's related or what's not related to one another. So this is an interesting object called the Accident, which was named by a citizen scientist who discovered it. It's very cold, like 500 Kelvin only. And we think that it's either a T-type halo dwarf or a Y-type halo dwarf. We don't know. We definitely know it's in the halo, but we don't know what spectral type it might be. And so we're approved to get JWST observations in cycle 2 to get a spectrum to understand what it is. Interestingly, this is the fastest moving object we found in terms of proper motion over the past 8 or so years of searching Ys for high proper motion objects. The total proper motion is about 2.7 arc seconds per year. So for comparison, Bernard's star is like 10 point something arc seconds per year. We were hoping to find something in the 10 arc seconds per year range, but we still haven't. But this is the fastest moving object we have, and we think it's a halo T dwarf or Y dwarf, very cold. Another recent discovery in this kind of space is that the first hypervelocity L-type subdwarf was found. So this is a little bit warmer than the T dwarfs, but it's interesting that L-type hypervelocity subdwarf was found at only a distance of 125 parsecs, which suggests there might be a big population of these out there. And that would be especially well suited for LSST, I think, because these are warmer, where LSST will excel more. And LSST can really push the distance limit out for L dwarfs. And so interestingly, it has this kind of like radially inward orbit that's almost unbound to the Milky Way. So if this object is what we think it is and is representative of a new population we haven't seen before, I would think LSST would be great for this because it does well for the warmer objects as opposed to the coldest brown dwarfs. And it'll just push our distance limit further out, so a bigger volume to probe. Another thing that's going to happen over the next year or so before LSST is that we recently got approved for a JWST Cycle 3 program to look at a couple dozen very cold and low metallicity brown dwarfs. And this is going to really teach us a lot about the spectroscopic sequence of these objects. Especially, it'll help to establish a classification scheme for the halo metallicity-ish T dwarfs, which we've never been able to do before. And so I think this will really help us to understand what we're looking at, given that right now we have such limited information. Now, the last LSST related thing I wanted to say is that a lot of the fun and excitement that's come out of this area of science, the brown dwarfs and also the halo cold object specifically, has come through a citizen science project called Backyard Worlds. And I think by now it's pretty clear that Backyard Worlds has demonstrated the efficacy of color and motion brown dwarf selection, leveraging a crowdsourced approach, by which I mean citizen science. And fortuitously, Rubin is building a convenient pipeline for uploading LSST data to Zooniverse. And so I think this is going to be a great opportunity to do something like we did with Backyard Worlds, which looks at WISE data, but with LSST data to sort of look for color and motion selected objects, be they brown dwarfs or specifically halo brown dwarfs. So I'll just leave some of the remaining major questions up. We still really need to look more into the model predicted colors of these halo T dwarfs and understand how they stand out or don't relative to other populations. It deserves more thought exactly how much weight we put on the motion versus the color selection when we do LSST selections of brown dwarfs and halo brown dwarfs specifically. The Euclid plus LSST combination is very interesting. Again, it brings in this motion versus color aspect as well, but it's nice that the depths are matched photometrically at least. And then one thing which I think LSST could help a lot with is the luminosity of these very cold and low metallicity objects, because right now we only have a parallax for one of them. But putting these things on some sort of luminosity scale would really help us to understand, like the volume density of these objects, or make predictions for how many we're going to see in different surveys like LSST, Roman, and Euclid. So thank you.
Over here on this side. Yeah, so in regards to the amount of contamination of background objects, this is something that was related to my PhD work. And we had some good results in taking proper motion data from, in this case, pan-stars, combining it with color selection in order to pull out, in our case, young brown dwarfs. So we were looking at them in clusters where we would look at the synchronized motion through the sky. But in this case, since you're already going to be limited compared to a lot of your contaminants and these objects being a lot closer and having large proper motion, I think that should give you some good results in terms of convincing you that it is at least not a very reddened source. So, I mean, are you, what's your feeling, I guess I would say, so far in how effective you think that might be in just having those higher proper motion values to be able to say, oh, these are not going to be background M giants or something?
Yeah, I mean, from our experience with WISE, the proper motion is the key, because you can have lots of red sources in WISE. So I think it's going to be key. The thing with proper motions is you have to wait a while to build them up from LSST alone. I know there's been a lot of interesting discussions about having like a DCAM 0 as ethics or something for LSST, which sky coverage wise by now is probably very close. So I would guess in the early days, there will be a lot of interest in combining with other data sets, if there are any that can rival the 6-month LSST data set over the same footprint to try to get the baseline.
Yeah. And I think in particular, because these are halo objects, I think they probably might stand out even more.
Yeah. Yeah, I mean, what was it, 160 milliarc seconds per year? That's pretty fast.
I wish I had those kinds of numbers. Yeah. Thank you.
I guess, I'm the chair, so I guess I can call on people.
Since you're working on a proposal with Oudenberg Gasser and you mentioned looking for companions to FG
Mhm.
and K stars, are these stars really low metallicity that you're looking companions for?
In that case, yes, but I think we're also just generally interested in looking for very low mass companions around any type of star because, as I said, we don't really have a good sense yet of like the multiplicity fraction as a function of these different parameters, like the type of the substellar companion or the separation of them between the host and the companion.
I know people have also looked at existing subdwarfs below Fe/H-1 for common proper motion pairs and haven't found any. So
Okay.
that's why I'm kind of interested.
I think they're not very low metallicity. I think they might be like a couple tenths below normal metallicity, but I'd have to look back at his proposal. I actually tried to look back at his proposal earlier today, but it seems that the STSCI system is down, possibly due to this cyber incident. So I was trying to look at that this morning.
And one more question. Given the fact that these would be really old, have you looked at the cooling times to estimate what their magnitudes would be? I mean, there's been models for low metallicity stars down below. In fact, they kind of cut off at 1/10 of a solar magnitude. So I was wondering if you've ever looked at those models.
Yeah, to be honest, I'm not the best person for knowing every exact model of brown dwarfs and what they include, but these low-Z models I was talking about, they don't include an evolutionary component with like a radius, for example. So you can't do actual magnitudes, you have to do colors like I was doing. Other people in the audience might know more about what state-of-the-art models are that have evolution and low metallicities, but I think there's not too much out there, if I'm remembering correctly.
Maybe 5-10 years ago,
Okay,
the best ones I know of.
okay, cool. Greg, do you have a?
Yeah, just a quick one. What are the prospects for getting more distances to the to those dwarfs from Euclid, from Raman, and combining that with LSST? Can you expand?
It's a little
beyond
bit-
hundreds of parsecs or so.
Well, certainly Roman will go much further out because it's just so deep, and it's like the same depths as LSST, but in the infrared. So Roman will go much further away, and it'll have a much larger volume, but it's also further in the future. Specifically with distances, the nice thing about LSST is that you have this repeated coverage, so you can do proper motions and parallaxes. My understanding is that Euclid doesn't have a very strong like time component in the sense of a time baseline and fixed sky location. And Roman, really the interest there is in the high latitude wide area survey, and I think that's still being defined exactly what they're going to do. I'm sure there's people who are going to want different things as far as time baseline and fixed sky location versus other trade-offs. So. DJ? Yeah, sorry, I don't know if I'm giving myself
Quick
extra time here.
Yeah, so for the James Webb programs, there are some kind of large programs that try to find some kind of high-Z quasars or galaxies, and brown dwarfs are usually kind of contaminants from all of those surveys. And also those objects have photometry and sometimes spectra. So probably some of them are like subdwarfs. I wonder if you have like plans to looking at those kind of data.
Yeah, that's a great point. There have been these deep extragalactic mainly surveys with JWST that are very small sky areas but super deep, and they're doing things like finding Y-type brown dwarfs, so temperatures less than 500 Kelvin, all the way out to of order like a kiloparsec, which is really amazing, and getting both photometry and spectra of them. So yeah, that's kind of like the one other way of coming at this problem is instead of going wide with LSST to go like really pointed and deep with JWST. But I was focusing on LSST because this is an LSST conference today. So I think I'd probably like to get off the stage, so I'm probably giving myself too much time now.
So he
Thank
doesn't
you.
have to say it. Can we thank the speaker?
And I think our next speaker is Easton Honaker, did I pronounce that correctly? From University of Delaware, who's gonna be talking about simulating solar neighborhood brown dwarfs more generally, a guide for future surveys, I presume including LSST.
Thank you, Aaron. As he said, my name is Easton Honaker. I'm a second-year graduate student working with Zhang at the University of Delaware. And today I'll tell you a little bit about my work simulating brown dwarfs in the solar neighborhood and their relation for LSST. So I want to guide this talk with three major questions. The first question is, how many brown dwarfs are there? How do brown dwarf populations vary across the galaxy? And what will these brown dwarfs look like in LSST? So the first step to get there is we have to talk about what is a brown dwarf. Aaron gave us a great introduction, but let's start this way where, let's move that off screen. If I put up everyone's favorite HR diagram with the main sequence going diagonally down to the right, we don't see brown dwarfs, right? And that's because these are cold substellar objects. So we're really talking about a mass range somewhere between 0.08 all the way down to 0.003 solar masses, very small. As far as temperatures go, that means we're looking at about 2400 Kelvin all the way down to maybe 300 Kelvin. So if you were to actually try and put these on the HR diagram, they'd sit here, off the chart. So we like to classify stars using spectral types. So at the bottom of our main sequence, you have the M dwarfs. Those are roughly above 2400 Kelvin. And once you go below the hydrogen fusion limit and you reach substellar status, you reach the first of the brown dwarf types, which are your L types from 2400 to roughly 1300 Kelvin. These are well characterized by that cloudy atmosphere you see. They're filled with silicate clouds. As you cool off, those silicate clouds will actually rain out of the atmosphere and you'll become a T dwarf and have a very clear atmosphere. These are roughly 1300 to 700 Kelvin. And if you go cooler than that, you reach Jupiter. Or at least that was the state until about a decade or so ago. And we more or less recently introduced the Y spectral type dwarfs, which are roughly below 700 Kelvin. These will be really well discovered with JWST in the near future. And so the field of brown dwarfs as a whole has been really driven by these digital sky surveys. In the optical, you had the Sloan Digital Sky Survey, Pan-STARRS, and Hubble, but because these are cold, faint objects, they show up really nicely in infrared. So Hubble's infrared, 2MASS, and WISE. And so the question now is, what can the Rubin Observatory and LSST bring to the table? A couple key points, this lovely picture of the camera, but it's the largest ground-based survey of all time. And over its 10-year co-added survey, it's going to be surveying the southern sky roughly below a declination of 15 degrees. And if you compare it to its closest predecessor, Pan-STARRS, it will reach at least 3 magnitudes deeper by the end of the 10-year co-added survey in the Z and the Y bands. And then everyone's favorite figure here, it's expected to resolve 17 billion point sources. Some of those have to be brown dwarfs, right? So back to these open questions. How am I going to try and answer those? And the way I'm going to do it is I'm going to use a synthetic population. I'm going to simulate a population of brown dwarfs around the sun. And to start, I use a base population. The base population to me has 5 components. It has counts. How many brown dwarfs are there? Position. Where are they? Ages, masses, and metallicities are some basic parameters. And of those 5, the last 2 are actually the most straightforward to figure out because we can use observational relations like the age metallicity relation from Daltio or the initial mass function from Kirkpatrick. The first 3 are a bit trickier. A relatively standard approach is you could use some sort of an exponential distribution for positions and then either a flat or an exponential birth rate to get ages. We went a different route, and recent analysis by Matzi et al. In 2024 and the trilegal team, they used the Gaia color magnitude diagram. And they looked at stars within a cylinder roughly centered around the sun that extends at 200 parsecs in radius and about a kiloparsec above and below the galactic plane. And what they did is they split that cylinder into slices that are parallel to the plane, 50 and 100 parsec slices, and they matched the stars in each of those slices with isochrones and worked backwards to get a star formation rate history. So what that gives us, from the Gaia color magnitude diagram, we have a star formation rate history that is a function of position above and below the galactic plane. So if we start from there, we can take our local slice with the sun inside of it, we can normalize it using the best at all 2024 brown dwarf spatial density, and then we can scale the remaining slices based off of relative star formation. And if you do that, you get a distribution of objects that looks like this. There's around 820,000 brown dwarfs just in that cylinder, the solar neighborhood alone. And if you look at this, it looks roughly exponential, but an advantage to our simulation is not exactly. There are slight anisotropies above and below the disk that come from the Gaia color magnitude diagrams we wouldn't otherwise have. Okay, so we've started to answer how many are there, but we can also look at how some of those like base parameters change. So for example, here's the age distribution. Now this is a rather unconventional plot, so I'll walk you through it. What I've done is for every one of those slices in the cylinder, I've created a violin plot that shows the age distribution. The upper row of panels is for the slices above the galactic plane. The lower row of panels is for slices below the galactic plane. And as you move from left to right, you're getting further and further away from the galactic plane. And so what this shows us is that slices close to the plane have very young populations, while slices very far from the plane have much, much older population. This is going to be an important thing to take into account as we start to probe further and deeper populations, and we realize that we have to work on these older groups. And so that also shows us that our local samples, we knew this already, but it really reinforces it, we're biased against younger populations right now. So this is starting to answer, how do we vary across the galaxy, but we can do a little better. So what we did is we used some evolutionary models. We interpolated our base population, and we got out parameters like temperature, luminosity, and radii. Specifically, we used two evolutionary models. We first used the Sonora Bobcat cloudless models. These are really good for those colder, cloudless, clear atmospheres T-dwarfs. But then we also used the Simon and Marley 2008 hybrid models, which for hotter temperatures start cloudy and then transition to cloudless. And so we can do the same thing I just did with age. We can use one of those other parameters. So I'm going to show you the luminosity function. The luminosity function is particularly important because it's what we're actually going to see, right? All the other parameters that we want to derive, like temperature, radius, come from us measuring the luminosity and then fitting it with an evolutionary model. So I've shown violin plots for each of the slices again. On the left-hand side of each slice is the blue Sonora Bobcat cloudless models, and on the right is the orange hybrid models. Remember, the upper panel is slices above the plane, bottom panels are below the plane, left to right is more distant from the plane. One feature I'd like to point out is this bump you see in the hybrid models, which starts, it's very significant at low heights and flattens out as you go further away from the plane. This is when the models transition from cloudy to cloudless atmospheres, and there's a slight pileup of objects. And so we can see that each of these slices has a different contribution. We can actually zoom in on these slices, and I can show you a slightly more detailed histogram. So the upper panels are the slice above the plane, the lower panels are below the plane, but that key feature there, it's strong, it gets smaller, and then it's almost gone. And so this is a really important thing to realize, because as we look further and further out, the luminosity function we'll observe is a composite of the luminosity functions in each of these slices out to that distance. So understanding how different slices contribute is very important. Okay, so I think we've answered that part a little more. And so that leaves us with one last question, is what will they look like in LSST? And to do this, we did synthetic observations. Now the Sonora Bobcat models have a grid of spectra. And so we're going to work with that set of population from here on out. We simulated observations using the LSST wide, fast, deep footprint, roughly anything below 15 degrees in declination, and the single visit and 10-year co-added photometric depths for the RI-ZY bands. And we said an object in our simulation would be observable if it's within the footprint and brighter than the filter limit. And so we did this for a subpopulation of T3 to T7 dwarfs in our synthetic population within 200 parsecs. That's because that's the best fit for the model, and also that's the largest symmetric volume we could do based on the cylinder we had. And so what I want to show on the far side here is, as you go out in distance, I'm plotting the number of objects detected in each band, the RI and ZY bands. In the solid lines, it's for a single visit. In the dashed lines, it's for the 10-year co-added survey. Out to about 25 parsecs, all four bands perform more or less the same. But the moment you start to go further, the Z and the Y bands significantly outpace the R and the I bands. And on the right is a completeness plot version out of the number of objects potentially detectable in the LSST footprint. And we see the same trend. They all do roughly the same. And as you go further out, the Z and the Y significantly outperform. Now, I'm going to put this up in numbers, and it's a little overwhelming. But as you go from left to right, it's the distances. The full sky is just how many of our objects in our simulation were within that distance, regardless of footprint. The LSST row tells you exactly how many of those objects would be in the LSST footprint. And then the remaining 4 rows are the counts, either for a single visit or for the 10-year co-added visits in the Z and the Y band. And that's a lot of numbers and it's hard to read. But what I really want to point out is the completeness percentages. And this really underscores the importance of the Z and the Y bands for brown dwarfs. With just a single visit, we'll have 100% completeness within the LSST footprint for T dwarfs out to 50 parsecs. And by the end of the 10-year co-added survey, we'll have nearly 100% completeness out to 200 parsecs. Most complete sample we have to date, 25 parsecs. That's huge. Last thing we did is we wanted to compare our simulated colors to observed colors. Unfortunately, we couldn't do that with LSST yet. So we did it with the closest thing we could, which was pan-stars. So in orange are observed pan-star colors from the ultra cool sheet. And in blue are our simulated colors. And we can see that in the T-dwarf sequence, they agree very nicely on the ZZY color magnitude diagram. However, when we introduce the R and the I bands and we go to color, and so here we have a corner plot with every color combination you can make with the R, I, and ZY bands. Our simulated blue colors don't match at all. Not even like the wrong parts, just not nowhere. So that's a problem. And we were looking at it a bit, and it turns out that this is because of the alkali elements that are really strong features for these cold dwarfs in the optical. And so specifically in my plot here, you can see the sodium and the potassium doublets are right on top of the R and the I bands. And because of collisional broadening with helium and hydrogen, they have these super wide wing features. And so when we don't have colors matching up, maybe we're mismodeling part of this. And so if we want to, like Aaron was talking about in his talk, develop some way to take these objects out in color space for LSST, this is an area of future work that needs to be emphasized. So with that, I'll leave you with some conclusions and I'll take questions.
Just a side comment, David Kirkpatrick was back in all 2016, 2017, had a paper out on modeling known spectra of warmer dwarfs like L and M. And one of the interesting things that happens for these stars is you can't match the fluxes in the infrared and the bluer colors. There's an opacity problem in all of the models. So that may also not just be the metals that you're worried about, but a real opacity difference that we haven't accounted for in the models.
Agreed.
So those numbers like 30,000, what range of spectral types were those for again?
The overall.
Yeah, you had like on the far side, you had like 34,000 or something in that one table.
I can go back to that table. So this one, right?
Yeah, what range is
This
spectral
is
types?
specifically for those T3 to T7 dwarfs.
Yeah, that's a lot of T-dwarfs.
And you had a question.
Yeah, very nice talk. I wanted to ask whether the metrics that are being used by the SCOC to evaluate science cases for brown dwarfs have been updated, you know, to reflect sort of your current work or
So my understanding, Zhang wrote one a couple of years ago with parallaxes specifically. But one of my plans for the summer was actually to start working on some sort of metric like this.
Okay, yeah.
See if we could pull something out of it, because this is a science case that really underscores the value of that Y-band photometry. So having some way to evaluate that would be really helpful.
Yeah, I think the time is sort of the essence now in order to make any adjustments to the filter balance.
Okay, let's thank Easton again. So our last speaker for this session is Zhang, UC Santa Cruz, is that?
All right. Okay, I'll start. Hello, everyone. I'm Zhang. I'm currently a postdoc from UC Santa Cruz. And starting from next year, I'm moving to University of Rochester as an assistant professor. So it's my pleasure to come here and share with you about some thoughts regarding like how we can find more planets and benchmark brown dwarfs by using large sky surveys, including LSST. So over the past few years, one of the exciting things in the astronomy from the space has been the launch of the JWST, the James Webb Space Telescope. And here is a combo like that I make for several kind of new science results enabled by the JWST. And apparently these results cover many different subviews like cosmology, galaxy, Milky Way, stars, planets, solar system. And given my personal bias about the excitement of the brown dwarf science, I'm pretty impressed by the spectroscopy that the James Webb provided us with. And this is for a brown dwarf called VHS 1256b. And as we can tell from the name, the system is actually discovered from the Vista Hamster survey. And the brown dwarf is this one, this kind of tiny dot, and it's a companion that orbits the star. And the James Webb basically provides an emission spectrum of this brown dwarf spanning from like 1 to 15 micron. And most part of this has never been observed before from the ground. And apparently all of these wiggles most of the wiggles are real, and they like tell partial story about the brown dwarf. And it's just by studying this kind of data that we can learn like atmospheric processes and compositions of the brown dwarfs. And the typical way that we extract all of this kind of information is by comparing the data with the models. But one of the current challenge of the in the field is that there's some kind of uncertainties on the theoretical models, and that is also like mentioned in the earlier talk in this session. And basically, like the models produced by different groups are sometimes not exactly the same. So in other words, our current understanding of the planets and brown dwarfs are highly model dependent. So what I'm going to show in this diagram is the emission spectrum of different models developed by different groups. And they're all developed at the same combination of parameters, the same composition, like solar value, same effective temperature, and same surface gravity. And this is a model, the first kind of model set, Udisetto. The second one, Snorre Diamondback, and this is the third one, exoplanets. So all of these models are state of the art. They're developed by different groups by using different assumptions. But what we can see here is like there's sometimes some kind of large differences among the model sets, right? And the flux is in log scale. So some of the difference can be half order magnitude. And given this kind of fact, we can see like the final kind of properties that we derive from the spectrum really depends on who we are asking, what kind of models we use. So to really move forward in the field, I think it's really important that we find some kind of empirical standards. And for these empirical standards, we hope that we know their fundamental properties reliably, and we can and if we directly observe their spectroscopy, they can tell us like what the spectrum should look like at that given combination parameter. So that's how the benchmark brown dwarfs chime in. So this is supposed to be an animation, and you will see a binary like orbing with each other. So basically, the benchmark brown dwarf is a kind of empirical anchors or standards for this purpose. And what is a benchmark brown dwarf? So specifically, I mean the brown dwarf that orbiting stars as companions. Okay. And the reason that they're empirical anchors is because the brown dwarf and star, they're born from this binary, so from the same material at the same time. So that means the properties of brown dwarfs can be independently obtained by studying their parent stars. So by analyzing the stars, we can know their compositions, we can know their ages, we know their distances thanks to Gaia. So that means for these brown dwarfs, we can know their effective temperature, surface gravity, and compositions as well. And for this kind of brown dwarf, if we directly observe their spectrum, we can understand like what the spectrum should look like at that parameter set. And one of the example is a work that I did earlier, and there's some kind of format issue, but that's fine. So this is a benchmark brown dwarf called Bros 450C, and the black is the data, and the green, ignore the blue one, the green is a model prediction. So basically that is a model generated at the parameter of this brown dwarf. And in the ideal world, we should see that the model and data should be exactly the same with each other, but apparently it is not, right? We see some kind of large differences, and actually all of these differences tell us some kind of ways or some kind of current quote unquote limitations of the models. And they can teach us like how we can further improve the models in the near future. And imagine like if we have a list of benchmark brown dwarfs, we'll be able to anchor the model prediction over a wide parameter space. So that means we want to find more these brown dwarf companions. And in order to find them, like large sky surveys are really important resources because they provide photometry and purple motions. The photometry allow us to know whether an object is a brown dwarf. For example, this one, this red dot. And also based on proper motion, we can know like whether they're co-moving together in the sky. So by the way, this is the image of, from the pan stars of like a pathfinder of LSST. And also like we have a lot of data in hand already, and also some kind of data, upcoming data. So Pan-STARRS provides optical data for 3 pi, like 3/4 of the sky. And there's some infrared survey from UKIS Hemisphere Survey, VISTA Hemisphere Survey, also CATWISE. Apparently, all of us are looking forward to the deep optical data to be provided by the LSST. So in order to verify the potential of this kind of large sky surveys, I have been leading a program called COCONUTS. So the full name is Cool Companions on Ultra Wide Orbits. So the goal here is like I make use of several existing large sky surveys like Pan-STARRS, 2MASS, UKIS, and ALLWISE, and I try to combine all of them together, use a photometry and proper motions to find some kind of wide orbit companions and learn what we can do with upcoming data like LSST. And this kind of a program is initiated when I was in Hawaii, so that's why it got a kind of refreshing name. So at first we get a large sample of the primary stars. So we got a total of 300,000 stars from Gaia DR2, which is available back in 2019. And then around each primary star, I search for all of the candidates within a certain range of the separation, like 10 to the 5th AU. And you can imagine, like, given all of these primary stars, we end up with a huge kind of list of the candidates. And then for each candidate, I combine the data from Pan-STARRS, 2MASS, UKIS, and ALLWISE. So in total, there are some kind of photometry over 10 bands. And also, we calculate the proper motions by using astrometry over like a 15-year baseline. And in order to find brown dwarfs, we focus on the brown dwarfs. So definition of the brown dwarfs is like, if they're young, if the whole star is young, then we try to find objects with spectra types later than M6. And if they're old, then later than L4. And the definition here is because the mass of the objects, like brown dwarfs, is really dependent on their ages. And in order to further shrink the list of candidates, I designed several kind of photometric criteria. One of the examples is here, like we look at the color diagram, and this is Y minus W1 and Z minus Y, and this is Pan-STARRS photometry. And all of the brown dwarf form the sequence like this. It's from M6 to L0, L5, and T dwarfs. And we try to find the candidates that follow this kind of sequence. And imagine like we do this kind of color cuts using like something like 30 different diagrams. And that basically shrink our candidate list from like a petabytes to terabytes and down to a short list of 1 megabyte, like 300-ish candidates. So the whole process sounds pretty straightforward, but it's really kind of tedious and complicated. So the next step is the exciting part, that is to confirm these discoveries. And to do that, I use all of the 4 telescopes here to gather proper motions and photometry and spectroscopy. The spectra is important because that can tell us whether an object is a brown dwarf or a gas giant exoplanet. So COCONUTS has found a lot of new kind of companions. And one of the examples are like COCONUTS-1. This is a rare system composed of white dwarf plus a brown dwarf. Also COCONUTS-3, which is a young M5 dwarf plus L6 brown dwarf. You might be thinking about like where's COCONUTS-2? And the COCONUTS-2 system is composed of a young M3 star with a T9 kind of planetary mass companion. The mass is about like 8 Jupiter mass. The planet to host a star mass ratio is about 0.002. So that kind of satisfies the IU working definition of the exoplanet. So you can call it exoplanet or planetary mass object or low mass brown dwarf based on your personal preference. This object is interesting because the planet is really close, like only at 10.9 parsec. It is the second coldest planetary mass companion and the second widest companion. These are examples of like what we can find by using existing large sky surveys. And beyond the 3 published ones, in total, we found 52 new benchmark brown dwarfs, and that can help us to anchor the models over a wide parameter space. And I'm now writing up a paper to publish all of these discoveries. So now I would like to talk about the LSST, like what we can find in the next few years with the deep data. So here, what I'm showing is the expected properties of the objects that we can find given the limited magnitudes of the LSST and other surveys. So this is a mass and as a function of vector temperatures. And different horizontal lines here represent isochrones based on Snore Bobcat models. The blue area basically quotes the typical sensitivity of the COCONUTS based on the data that the COCONUTS used. And again, all of these are like within 100 parsec, and I assume a typical distance of 70 parsec. So the lower boundary of the blue area is defined by the 10 million years because within 100 parsec, basically the youngest object is about 10 million years. And this kind of boundary is basically defined by the limiting magnitudes of the Y band of the pan stars and also the W2 bands of the all Ys. And given the LSST will have a deeper Y band data, if we combine the LSST Y band plus like J band in the Vista hemisphere survey, we'll be able to push the boundary to the colder effective temperatures. And that will give us some kind of a room for the lower mass companions. And this is at 70 parsec, and this kind of boundary will be toward the even colder temperature if this closer distance. And in addition, if we further expand this kind of diagram to farther distance, like 200 parsec, we'll be able to search for more objects in the young star-forming regions, right? At 140 parsec, there's a Scosen and also Wolf-Fucus. So that will further push down the boundary to around 1 million years and also define the boundary here in the temperature. And I have done the calculation, like if we have 10-year based LSST data based on Y band and plus a Euclid J band with a deep kind of images, then we'll be able to push the boundary to around 500 Kelvin in the effective temperature. And that will give us some kind of sub-Jupiter mass companions. So, so this is basically the idea that I have, like we can use this kind of upcoming data to search for more benchmark ground dwarfs. And I'm really happy to chat about this and also in collaboration if you're interested. So please discuss with me offline. But with all of this, I will just stop here and ready for questions.
I can ask a question. I guess I'm looking at this, maybe I'm interpreting it wrong, but is it saying that as you go to younger ages, you can push to lower temperatures for what you can detect in these surveys, like with LSST plus VHS? Okay, yeah, I'm not sure. Yeah, I'm not sure I would have guessed that, right? Because there's like, sometimes there's conventional wisdom out there about like the blue L subdwarfs and the blue T subdwarfs, in which case, that's a narrative of like things get bluer as you get older. But here it seems more like you're somehow shifting more flux, a little bit shorter wavelength as you get younger for fixed temperature or something like that.
I think here is basically like if you go to younger things, the boundary will not change so much in the effective temperature because it's basically vertical. Right? I think what changed the masses is basically like the age definitely matter for the mass, but not the effective temperature.
Yeah. Okay, well, if there's no other questions, we could have any general discussion people want to have in the last extra 8 minutes here about stellar Milky Way type science with LSST or anything we heard about today, or we could end a few minutes early since I know that that's basically what we planned for, to have a little bit of buffer in the schedule. So let's thank CJ again. I don't think we did that. And we can open it for discussion or we can call it a session 7 minutes early. Seems like maybe people are tired from the first day. So thanks a lot for attending. Thanks to all the speakers for keeping us on schedule. And yeah, look forward to the rest of the meeting in the next few days. Thanks everyone.